Okay. Okay. Yeah. Okay. Okay. So thanks to organizers for the invitation. I think we really want to be here with the CORSIKA 8 project to give you an update of where we are. So with what we're really seeing it is now, that's why the title is really Beyond Air Showers. We can do more things than just simulating cascades in air as CORSIKA 7 was doing, and there is a motivation for looking at those things. But one thing, what is important, why we're worrying about this is that CORSIKA 7 is by now showing its age. It's been written or started over 30 years ago in Fortran with different dialects of Fortran. The code has been hand optimized. Some of the code options come through conditional compilation, so it's not really easy to extract the code and understand what is going on and to maintain it. There are some design limits which are hard to overcome. Some of the key developers have retired and handed over the code, and it's not always easy for the new people to really understand in depth. I think Tanguy has been doing heroic effort to keep CORSIKA 7 alive for the community. So, but we also noticed when we look at the current generation of developers, Fortran is really not a skill that most people learn and have or want to pick up, even if they could. So what you find when you look at any of the collaboration at the new generation, people would love to do it in Python, which just doesn't give you the speed for a project like this, and then grudgingly accept that they have to code it in C++. So this is where we've been going. So some of the things, if you look at some of the CORSIKA 7 use, you get complicated pipelines where adapters connected to adapters to things. So it works if you know how to do it, but it's not always beautiful, not always very simple. So so we're looking for a successor that allows it to make it easier to integrate things that's been designed as a framework. Another thing which is important, the community needs standard tools so we can focus on science. We don't want to fight about which tool is the most beautiful to use when we come to do analysis. You've seen a couple of examples, for example, in John's talk, by looking at standard tools like when Auger and TA started to put their basic tools together, all of a sudden a lot of the discrepancies went away, and you could look at the real science difference that we discussed instead of getting artifacts from the fact that different groups use different tools. So it's really important to have different tools. It has to be well designed. You don't want to use your spork and then cut yourself on the handle. So this is important when you have tools. You need documentation, so you actually know whether you use a hammer or a screw for the problem that a hammer or a screwdriver for the problem that you want to solve. So this is all part of what we've been looking at it. We need documentation, community experience that at the end helps everybody. So this is part of why we're still struggling. So what is it really why we're doing CORSIKA 8? I mean, it's a project that started in 2018, pre-pandemic, with lots of optimism that it would be fast and easy to do. It turned out to be a bit slower than we wanted to. The design was, pandemic obviously slowed us down. It's designed as a framework, so you really have an API and pluggable modules. So this is what should allow you to have pipelines that are manageable instead of having to figure out how to get to somewhere and connect things in a more ad hoc way. So that should simplify extensions, and we'll see some of the different things. One of the things which is special for CORSIKA is it looks at large geometries like an atmosphere. So this is why you can't just go and say, oh, we have Geant 4 as a framework. You need some more optimizations. For example, continuous changes in volumes of material, where in Geant you would just piece things together with constant properties. The point, we're using modern C++. We're at this point, so like looking into standard version 17, and probably would like to go to 20 at some point. But there are different concerns that I'll later mention. it's anticipate that it runs on modern high performance computers. So we want to be able to have different forms of parallelism with MPI, multi-threading. Accelerator support is relevant. So we're looking at all of this. It's designed from the beginning as a community effort. So we're trying to get people from different communities to understand the use cases. So it's not just what I need, but it's what we all need. That's driving us. So we're listening to people, and we often during the meetings have people from other communities pop in and say, okay, look, we're doing this. We would like to use this, or we've started to see that with CORSIKA 8, we can do something which we couldn't do before. So the design is pretty standard, similar to, you have the main cascade, you do particle tracking, you have to have the environment, then you have the physics process, which are different type of what happens during the interaction, and you process them, and then you try to provide some sort of standard output that you can use for post-processing if you're, because at some point you can't do it in CORSIKA, even if we try to make it universal, at some point your detector will be special and you can't, you might be able to connect it straight to CORSIKA. It might be easier to connect it through standard output level. So we provide both possibilities in the project. And the status is, it's at this point, we would say physics complete. So you can basically simulate all that you could, or do more than what you could do with CORSIKA 7. So you can do hadronic and electromagnetic air showers. You have from the beginning radio fluorescence emissions in there at first class citizens, not something that gets added later on. There are several of the important or new features that, for instance, like we have all the standard high energy models that you want to use. EPOS, QGIS, Sybil, you've heard already here that Pythia 8.3 is becoming, looking into the high energy model domain for us. So we have the possibility to work with Pythia. You heard that Clover was looking into that too. As a low energy model, we have now standardized on Fluka. Fortunately, Albert Ferrari offered us a more easy distribution channel for Fluka, so we can distribute it with the rest. So you don't have to do this, what people are used to and suffering from CORSIKA 7, download it separately, install it, and so on. So that should be easier in the future. And that was a key point for why we could really decide that Fluka is the one model that we're going to use. For electromagnetic interactions, we use the new proposal model that's been developed in the Dortmund group. And we're using it for a lot of the things at the beginning. We have thinning implemented. We have, as I said, chunk of light emissions with possibility parallel. We have the radio emissions in there. We have a demonstrator, but not yet a production-ready version of parallelizing radio emission to speed up that process. We have by now simulation steering. Before you had to do it with compiling the code the way you wanted as a framework, which was good for testing that the things work internally, but you don't want to recompile your code or set constant in the code when you do it. So we have steering down there, and we've done extensive validation against CORSIKA 7 when we really try to see that we either understand difference or preferably don't have differences, so you can reproduce the old results. And I'll show you a few of those validations later on. So the activities is we have our regular developer calls and developer workshop. We had one last year in June. We're planning one in September this year. Again, we had a few workshops before which were more open, not just developers focused. But right now, our greatest worry is that we've been promising a public beta release for general use for over a year. So the focus right now of these workshops is that the developers sit together and we try to make progress. Right now, we hope that we can get a sprint to get a public beta out later on this year. As I said, it's physics complete. We can do applications beyond CORSIKA 7. One of the things which the beta will be suffering from, it won't have the speed of CORSIKA 7 for standard applications yet. We know that, but at the moment, the physics completeness is more important than the speed. Once we have the code that knows work, we can start looking at optimizing it. If we have the code that gives you the wrong result, but very fast, that's not something you'll be interested in. So that's why correctness is priority before speed. As I mentioned before, we are a community effort, so new developers are welcome. We need skills of different persons for what we want to do. And as I mentioned before, we're looking for new applications. So that comes only with the ideas and requirements that other communities can bring. So people are welcome to contact us later on. I have the URLs and information for contacts. So this is a couple of us from at the last meeting in KIT about a year ago. There you see Ralf Ulrich here at the back, who is the person who originally pushed the project very much. There is, let's see, here's Max, who did a lot of the coding from the beginning, and Nico did a lot of the coding for the radio setting. These are the great heroes who made the project, pushed the project. Everybody else has done. I know here there's Marco. Those are the people from the proposal group. Everybody is doing things, but I think those deserve a special highlight in terms of without them, we wouldn't be where we are at this point. Tim is right now here, the project coordinator, after Ralf decided to drop out. So I think just those deserve recognition. So as I said, we've done extensive validations. The first part is the electromagnetic cascade. The CORSIKA 7 used a modified EGS code. We couldn't even get a proper documentation or manuals for this when we looked at CORSIKA 8. It's a Fortran code, so there were many reasons why we could not keep on doing that. We looked around, and then fortunately the proposal group came up with volunteer to participate in that project. So we used that code that had already been validated for electromagnetic interactions, and it's a more modern general purpose electromagnetic simulation code. And we've checked this here, for example, in a purely electromagnetic cascade and you see there are basically no really big difference. If you see the ratio, they're basically flat around 1, both for simulations of longitudinal profiles and charged particles or in photons. So we really reproduce the physics with a change of model. And then also when you look at energy spectrum and at lateral distributions, again, we have slightly bigger discrepancies, but in general, not too bad here. There's still a little bit of work ongoing to get this really, really perfectly flat. You see here that this doesn't quite follow the 1 as much as we would have liked, but it's tolerable. The thinning is a new algorithm that mixes the existing ideas to do Hiller's thinning and statistical thinning. That was important. At the early versions, we didn't have that, and we couldn't go to high energies. Without the thinning, high energy simulations would just not finish in a reasonable amount of time. The new thinning has nicer narrow distributions. If you compare the CORSIKA 7, the dashed curve, with the solid CORSIKA 8 curves, you realize we have most weights that pile up strongly at the maximum and don't spread out over a large range as they do for CORSIKA 7. That is in general good for reducing fluctuations compared to the old. So we believe that it's an improvement, the new thinning. We've done studies of hadronic showers. There, obviously, the comparison has to be done as a function of the different modules. Again, the dotted lines is CORSIKA 7. Here, the dot line is CORSIKA 7. The solid is CORSIKA 8. And the colors indicate which model you use. You can see here that the curves coincide. And if you look at the ratio plots, you see again, the differences are in general below 10%. Maybe at the maximum, they go up to about 20. The exact difference depends on the interaction model we're using. So, and we're doing more tests. We're especially redoing some of the validations which we've done before for the last ICRC to make sure that there isn't something that crept in and changes between then and now that we're putting out the release. And what we've also done in the past, we haven't documented our tests that well, so we're trying to get this also reproducible, that anybody else who's looking at this knows how we validate it, and if they come up with odd results. They can actually look at how their test is different from what we think is the right way of testing. We don't want to have lots of people coming, oh, our results look different. It turns out that they just didn't do the validation the way we think it should be done. So documentation of the code, and the validation procedure, both are important for the project and to avoid frustration and misunderstandings. There is GPU accelerated light emission for Cherenkov light. This has been largely motivated by the Ice Cube collaborators that really needs to do it. But it's useful also for imaging Cherenkov telescopes. There's also a simplified version to do the same with fluorescence, which at this point is more a proof of concept and for debugging, not yet optimized that we could use that in production. But it's really helpful when you produce lots of Cherenkov or fluorescence photons that you have to track. So they're having an accelerator GPU to support the tracking, speed it up is quite useful. It's been validated against similar versions that have been written for CORSIKA 7. So there's actually common code between those two projects for this acceleration. So, and it's not yet been fully integrated into CORSIKA 8. So this has not yet been linked as a first-class citizen, but it uses CORSIKA as a framework and as an add-on. How we distribute this is still a question how we integrate it, because not everybody has the same level of GPU and GPU accelerators, and you don't want to depend on the presence of a GPU. CORSIKA 8 has to work on a normal computer and then benefit from whatever accelerators you can add to it. The radio part has really improved a lot. So here I'm taking slides that colleagues have been showing at the Arena workshop just a few weeks ago. So this is quite impressive. If you look at the pulse shapes here by going in sufficiently small steps in different frequency ranges. So this is for a 1 PV vertical shower. And if you look at the pulse shapes in different models, you have the CORSIKA 7, which has the Koreas, but then you have in CORSIKA 8, both the Koreas and the ZHS formalism, which also exists in Iris ZHS, but not in CORSIKA 7. So you can see that all three formalisms really give you basically identically looking pulses here in the east-west polarization and in the north-south polarization of a simulated antenna. So that is really, really good news. So I think the radio part is understood, both between the transport course, CORSIKA 7 and 8, and between the radio emission modeling of Koreas versus ZHS as different formalisms. The same if you look at a higher frequency in a range from 50 to 350 megahertz, and you see again different processes besides the formalisms. You see the geomagnetic part, which is basically a synchrotron in the Earth magnetic field, and you see the charge axis, which is the separation of the positive charge parts and the negative parts, because the positrons and the electrons they get differently delayed in the atmosphere. So you get this as an effect. They produce different pulse shapes. If you look at what you measure is the overlap, but you understand both parts well, and they're both well simulated in CORSIKA 8. And you see this in fluence maps. This is a great improvement compared to what we've seen a year ago at the ICRC. By now, basically, if you compare the fluence map, they're almost identical by either small differences, but you see them here in the different components. This is the total flux, and then the different components, vertical, perpendicular to the propagation axis. They're basically coincide between what CORSIKA 8 has with the two different models and CORSIKA 7 here in both frequency bands that we're looking at. So I think we're pretty happy to say that the radio part is also understood and well implemented and tested. What we have is, what is really new is cross-media showers. There are different applications where a cascade will propagate not just in air, an example which you mightn't necessarily do in CORSIKA completely is, for example, the earth skimming neutrinos, where you have something that goes either through a mountain or just grazing here. I don't have the great geometry, would just go up, slightly propagate under the surface of the earth, and then come out. In both cases, you get cascades, and you have different levels of the geometry, which isn't just pure air. So you would do this for horizontal showers. The more interesting application is for for in ice showers. This is something which IceCube is interested, but also several of the experiments that put radio antenna in ice, which would really want to have the combination of radio emission and the continuation of the propagation in ice. So you have a profile, we have a high density. So I had to turn this graph around on the side to make it. So the high density in the ice, and then the exponential decay in the atmosphere. If you realize this is a logarithmic scale, so this is really the exponential density profile of an atmosphere that you see there. So you would have a propagation of your cascade from the atmosphere to ice. You get the jump in the density profile, and you see here how the different particle numbers change. This discontinuity here, this kink is really physics. This corresponds to the fact that because of the higher density, unstable hadrons now all of a sudden interact and don't decay. So because you always have this competition between mean free path for decay, mean free path for interaction. By having higher density, you get more interaction, so which would produce more hadrons. This is why you get something here that all of a sudden the number of hadrons goes up. So this is understood. This is not an artifact or a bug. So this is really the different density of the medium that causes that. This has been simulated here for showers. I'll show the next one. This was the illustration from the ICRC. If you look at what we have now, this has been verified by the colleagues from Uppsala who are working on this, on the, what's the radio one, the antenna in Greenland experiment. So they've been doing extensive simulation and verification. So you see really here the different codes produce really identical looking showers. So I think this is it's much better understood than it was a year ago. Here you have slightly different, slight difference, but again, the code is really well understood. This is what we wanted to integrate. Before in CORSIKA 7, you really had to patch the propagation in air with a propagation, basically had to dump at the surface and then reinsert into propagation in ice. Now you can do this in one code, which makes the simulation a lot easier to run. And you make sure that you don't have different codes that do the rest of the propagation interaction. It's just the medium that changes. There are people, this is new, I don't have that much detail, which was also presented at ARENA. People are starting to look again at neutrino cascade-induced acoustic pulses. So they've done simulations here. This is just a proof of concept that you can do this by going to CORSIKA 8. So their summary is that that it works, and that there'll be a module eventually that to allow this in CORSIKA 8. There are interesting other applications. Some things people approach us that they have. Oops, what did it do? To look at, they have some space missions. They want to look at some reacceleration and modeling of cascades in I think, I don't know if it was Neptune, Uranus, and some of the gas giants. Obviously, CORSIKA 7 is not set up for this. In CORSIKA 8, you can produce even such exotic atmospheres. Or the Tambo project, which is looking for horizontal tau neutrinos that come out of one wall in the Colca Canyon, and then have a detector on the other side. This would work nicely. So these are things that we're trying to support with CORSIKA 8, which couldn't be done in CORSIKA 7. So what we have to work on before the beta release is user documentation. We would like to have the reference papers out. We're looking into radio paper and the general paper that people can refer to when they say we use CORSIKA 8. The physics validation is pretty much finished, but ongoing. we're looking at how we distribute the code, that you get standard CORSIKA 8 binary or easy to build 8 binary, but also the framework as a build kit for experts. If you want to do something which is not anticipated and you want to use the framework, that we can support this, improving the external package management. So your CORSIKA, like most modern C++ codes, depends on a number of externals. You don't want to hand install everything yourself. But we also want to control the version, so our validation is easier to do. We want to have it containerized, so it's easy to share. So here, this is the collaboration. I just put up here the names, the steering committee, who and the people who really do, who all part of the collaboration. Yeah, and that's what I have. No, there was one slide. I don't know where it is. The conclusions. Yes, I was wondering where they ended up. So it's physics complete, so we can simulate basically all that we could do in CORSIKA 7. Radio emission is a first-class citizen. We can go beyond CORSIKA 7. Here is the link that I promised if you're interested in the project. Especially the first link is relevant. We are right now using a GitLab instance at the Institute of Astrophysics, but we're trying to migrate into a new GitLab at KIT, centrally managed. So this URL is not going to be valid for forever. The first one should be valid for a long time. And as I said, the first public beta is in progress, and we're looking at, and speed up is one of the things that we do worry about, that has to be done before you can do really, really mass production with CORSIKA 8. So thank you very much. So.
Thank you, Lukas, for the nice overview. Really nice to see this impressive progress. Are there questions or comments?
So Lukas, could you go to slide 8 about the proposal implementation versus EGS? There are some there are some differences, right?
Yes.
Particular in the energy spectrum and also for the distance to the shower core, the particle density. Yes. So do you know, is this just different physics implementation in proposal versus EGS, or is this some other reason?
I think this is different physics, and there was at some point, I don't remember, these were the slides from the ICRC, so I don't have updated slides from this year. So we're looking into what's the current status. Part of the problem, as I mentioned, we didn't know exactly what was the configuration when we did those plots. So we're looking at if the things are really still that discrepant with the current version. As I said, we're still looking into this. But I think there is a bit of physics change between proposal and EGS, and I think there was also problems of some of the cross sections we use from proposal, some other things. So so there were improvements in the last year of how we link into the code.
Okay.
Thank you, Lukas. It's great to see all this. It's very exciting. Just have one small question. Is there any option in that you would find in CORSIKA 7 that you have to abandon into the transition to CORSIKA 8? Because there were so many in CORSIKA 7, but maybe there are some that cannot be implemented now.
I don't think so, because it's a framework. It's actually more flexible, and if there's something that we have improved thinning, multiple thinning. We have the geometry is flexible, so the interaction models are there. So I think the options are there. We'll probably have an easier way to configure it. We're still looking into what gets runtime, what gets compile time configured for, because for runtime configuration is easier for the user. Compile time configuration might run a bit faster. So this is where we're looking at. We have now a full steering that we can do things at runtime, whether it's always the best or whether you pre-configure them. Especially when you want to do mass production for one particular configuration, you might be better off tuning it. That's still, we're still looking at it.
Okay, so we should expect the same options and even more, basically. Okay.
Yeah.
Awesome. Thank you.
Is there another question?
Actually, one of the options that is gone away is URQMD. I think we've dropped that from the list.
Ralf?
Yeah. I think the effort is enormous, and Lukas, you have shown it here. But I want to say there's still a long way to go for what you mentioned in the performance. So it's not like a 20 or 30% speed up that is needed. It's much more. And so if somebody really wants to work on it, that's desperately needed, because right now everybody has written things to the best knowledge, but that comes with a price. And it's so I don't know how we continue from there, because it might be in the end a real bottleneck that the things are too slow here. And we will have to see how to deal with this.
Yeah, we're looking at this, we're discussing this. And one thing that is important, speed up doesn't mean that wall time speed up, it means computing resource speed up. So parallelizing might mean that the code runs faster. So instead of a week, you do it in a day, but you still need the same amount of CPU cycles. So if you do a mass production where you need 100 years of CPU time, you don't want to have all of a sudden 500 years of CPU time. So there's really speed up in the code needed that isn't just done by saying, oh, parallel will run faster. That's only true for wall time. That's not true for computing resource usage.
Yeah, and some of the things, I mean, this version of CORSIKA is much better random number generation, like you can start at arbitrary seeds in between and whatever, but it all comes at a cost. And so some of the things you don't want to give up. And but if we in the end have only a factor of 2 in speed, it's all right. But we are not there.
No,
that's much more.
Yeah, this is what we're unhappy about. But we've decided that getting it out for people to look at is more important than getting a fast version out. If we can't just sit on the beta and keep on promising things forever.
Thanks for your presentation. Maybe you already mentioned that, I didn't quite catch it. So you said that you're enabling GPU processing for real-time analysis, or you just store the data and then you offline use those GPUs?
There is no real time, because this is a simulation process. So the GPUs would be running for some of the part in parallel to with the code. That the most likely is some kind of distributed slave processing for certain processes that you offload to the GPU, which are highly parallelizable. Because some of the things like parallel photon propagation is something which works well on GPUs. Normally, if you have things that has a lot of decision making with Monte Carlo code, you get so many different branches that there's this parallel way of how a GPU wants to do things. Lots of cores doing the same thing doesn't really work terribly well on GPUs. It's really difficult to get that kind of processing done on GPUs. So you need the mix of the two.
Thank you.
Yes.
Just combining these two comments, long back we attempted profiling the CORSIKA code, which part took more time. In fact, it was the random number generator. So let's say the random number generator can be done with the GPU and the rest of the process can be done with the CPU. Then there is a possibility that it can be improved, because as you said, GPUs cannot do well with the decision making.
Yeah, so we're looking into what causes. We've also found out it's not easy to do the profiling, because to do an honest profiling, you have to compile the code with optimization. But when the code is fully optimized, then it's difficult to track which position in the binary corresponds to which position in the source code where you optimize.
Yeah.
So it's also for us a bit of a learning process to really make best use of the profiling tools to really understand things. I think we had some red herrings thrown up in the first tests where we profiled code that was not optimized, and then obviously things that are trivially optimized by the compiler were actually not optimized and took a lot of time. So this has to be done careful and in discussion with experts. And there, I think we really could use people with a stronger computer science background. We are physicists, so we know what we want to do and how to get it right. but we don't have all the in-depth experience with all the tooling which a software engineer for high performance computing would have.
You know, in India, we had the same problem, like especially developing various interfaces. So what we did was we tied up with some of the engineering schools and offered them as projects. So that is one model you could think of, because those are really bright kids. They want to solve, but you have to be very specific what you want them to solve. And then they can do all the hard work and deliver you a finished module. All right. I don't see any more questions. No questions online? No. All right. Then let's thank Lukas again for this nice talk.
Okay, thank you, Lucas. Two quick announcements. First is, of course, the general comment dinner at 7 p.m. outside. Again, everybody is welcome. People stay in the Fiesta Americana don't need to pay. Outside, it's $55. Pay in the front desk in the hotel. We have a reserve table for all members of this event, so no problem. And just only need to go to make the payment and get the bracelet in the hotel reception desk. This is general, and I hope to see all of you or many of you at the dinner at 7 p.m. And a more local announcement, members of the IAC, International Advising Committee, we are going to have a short meeting in the office that it is upstairs. You go outside. Upstairs, there is a door in glass, and inside we are going to have a little meeting. So we wait only for members of the International Advising Committee. Let's thank all the speakers of the session and see you tomorrow.